What I'll do is I'll start with the general area or general subject of isotope separation, and uranium enrichment is a form of isotope separation that, for our purposes, is by far the most important. But in general, it's a technology that's very hard to master. And the problem is you're trying to separate two isotopes of the same element. And so they have different atomic weights, but they have the same number of protons. And so their chemical properties are the same. And so the traditional methods of separating substances just don't work when you're trying to separate two isotopes. We'll rarely use the term or phrase isotope separation here, but it is typically we're going to call it enrichment. And the idea is to increase the fraction of the desirable isotope. And I want to discuss three elements: deuterium, lithium-6, and uranium-235. Has everyone heard of deuterium? Mm-hmm. So anyone who's never heard of it? Okay, all right. So it's a stable hydrogen isotope, so it has 2 neutrons and 1 proton. There's also another isotope of hydrogen that's important, tritium, which has 3 neutrons and 1 proton. And both deuterium and tritium are very important in nuclear weapons. And deuterium is stable, tritium is radioactive. But deuterium is stable, but its natural occurrence is 0.015%. And the deuterium is typically in a water form, D2O. So you find it in essentially the ocean, mostly. And after it's concentrated, it's called heavy water. And it's a moderator for a reactor, as you know. And it allows the use of natural uranium fuel. It's a very good moderator. And so you don't have to have enriched uranium when you have a heavy water moderator. So the Iraq reactor in Iran is a heavy water reactor that was designed to use natural uranium. And any reactor like this with heavy water moderator could also use enriched uranium. So you can do that, but it is one type that allows the use of natural uranium. It also has a very important role in thermonuclear weapons. And typically in a nuclear weapon, it's going to, I'm sorry?
They can boost them.
Well, that's one application. So, but the main main reaction that's going on is deuterium and tritium are fusing. And so they'll fuse more easily than, let's say, deuterium and deuterium. And deuterium has found a useful purpose in what's called a long shelf life neutron initiator. And neutron initiators in a crude device is something found at the center of the core. And you would actually in a solid core device, there'd be a little hole, and you would stick a neutron initiator in it. And the idea is that when the fissile material compresses, you'll design it so that there'll be a reaction. And in the Manhattan Project and in several other bomb programs, they used one called a polonium-beryllium neutron initiator, and the radioactive material is polonium-210. And it has a big disadvantage that it has a short half-life. And so if you're going to use it as a neutron initiator, you have to replace it about once a year. And so another type, which involves deuterium, what you have is it's like a pellet of deuterium with another chemical, and it is a solid, and it's not radioactive, so it's a long-lived material. And what you're doing is using high explosive pressure, essentially, to compress the deuterium pellet, and it causes the fusion of deuterium with itself. And when that happens, when you get this fusion, thermonuclear fusion, it releases neutrons. And so through this it's a very inefficient fusion reaction. You get enough neutrons to start the chain reaction. And in proliferation, it's important because it was a design that China gave to Pakistan, and part of a bomb design that they gave in the early 80s. Pakistan spread it to Libya. We think they spread it to North Korea, and it's become a standard now as a neutron initiator. And for the longest time, its existence was classified in the United States. I mean, you'd actually see it written about in Chinese publications around 1990, but at that time, U.S. people with security clearances weren't even allowed to talk about it. It does require the design to work better than it would have to normally if it had like a beryllium polonium neutron initiator, because you've got to get this deuterium diffuse, which is not easy to do. So your implosion system tends to have to work better. It's produced in many ways. I'm not going to go through the details. If you want to look it up, I put in the names of things. This is a Girdler sulfide process, and then there's another distillation process. And really what you're doing is purifying the tritium in steps. And the goal is to produce what they call nuclear grade deuterium, which is 99.75% deuterium. And here's the picture of the Iraq heavy water production plant. And it's when you see this, and you can see it in satellite images, these towers are very distinctive, these columns, where you're doing the actual separation. And it involves heat and steam. And so from commercial satellite imagery, the columns can show up quite easily. And this would be one of the few cases where you can look at it and say, oh yeah, I know what that is. It's a heavy water production plant. But after class, if you look at it, you can. Here's an old picture we have of Pakistan's. So we were able to identify this from this image when it was still a secret site, and it was easy to give the purpose of it. Another important isotope is lithium-6, and it's a stable isotope, and it has a natural abundance of 7.56%. And you typically try to enrich it anywhere from 40 to 95%. And what you want it for is it's a natural material to irradiate with neutrons to produce tritium. And so you can use it in a couple different ways. I talked about using targets. You can make a lithium-6 target, put it in a reactor, and make tritium that way. And for the U.S., they need a lot of tritium for nuclear weapons. And they actually irradiate the lithium-6 in commercial nuclear power reactors. They no longer have any military production reactors, and they don't need any more plutonium. Another use of it is you can stick it into thermonuclear weapons designs, and during the atomic and the fusion reactions, you get a tremendous number of neutrons, which then irradiate the lithium-6 and make more tritium, which then fuses with more deuterium. Because you can't load up a thermonuclear weapon with tritium. So you can load it up with deuterium and lithium, which are stable, but you're actually producing a lot of the tritium during the explosion itself. It also has a notorious history. It was made down in Oak Ridge, and it was a mercury-based system, and we made a lot of it, and it was a time when industrial safety standards were pretty bad, and it's done through this Colex process, and essentially what you're doing is the lithium is dissolved in the mercury, and then it's reacted with water, it'll start to separate. The lithium isotopes will separate, but you end up with massive amounts of mercury. And a lot of that got into the environment down there. So, you know, it's a very toxic substance. But the main isotope we're going to work with is uranium-235. And again, just as a definition, the concentration of uranium-235 above its natural value is called uranium enrichment. That's all that means. And natural uranium has three principal isotopes. There's actually some others, but the three that are talked about are uranium-234 and the other two that you know, 235 and 238. And you also know that it's 3 to 5% in uranium-235 is great for use in power reactors, and for weapons you want to get it to 90%. Now I talked about this, I believe, the first week, critical mass, that it's the smallest amount of enriched uranium that can maintain or sustain a chain reaction. And for enriched uranium, the critical mass depends on the fraction of uranium-235. So we talked about low enriched uranium, high enriched uranium. This slide shows the critical mass as a percentage, or related to the percentage of uranium-235. And in this case, it's a sphere. That's the best, most compact form or volume you can get compared to a square or an ellipsoid. And it also has these numbers depend on having a reflector, some kind of reflector around it. So the neutrons, when they come out of the core, a fraction will bounce back into the core. And a neutron reflector is always going to happen in a nuclear weapon because you're going to have the high explosives, and the high explosives act as a neutron reflector. If you had 100% uranium-235, which is very, very hard to get, it's the critical mass, and it's called a bare sphere critical mass, is 15 kilograms, and then it just goes up from there. And I think I mentioned that anything you can get a critical mass down to about 10%, but you're required to get so much that no one thinks you can make it into a nuclear explosive. And so they arbitrarily drove the line at 250 kilograms because they figured that somebody could make a bomb out of that. It's, you know, I don't know how big it would be. It would be huge, but that was the limit. And so this is the logic of deciding what is low enriched uranium versus high enriched uranium. Now there's a zillion ways to enrich uranium. I mean, and the initial ones were unbelievably inefficient and expensive, and many just would never be economical. But there's all kinds of ways to do it, and I want to cover several types. And the first one that was deployed on a massive scale was used electromagnetic isotope separation method, and it was developed in the Manhattan Project in World War II. And it was also duplicated and modified in the 1990s, in the 1980s. That's wrong. It should be 1980s, Iraqi nuclear weapons effort. This is a Bush administration slide. But it should be the 1980s Iraqi nuclear weapons effort. And it wasn't finished in January of '91 when the bombing started. But it would have succeeded. I mean, but it was terribly inefficient. And for the U.S., it's what produced the HEU that was used in the Hiroshima bomb. That no other enrichment method was ready to make HEU by August 1945. And some pictures of it are here. Or here's a schematic. And the idea is that you ionize the uranium, so it's charged, and you shoot it through a magnetic field. Because the masses are different, it'll follow, each isotope will follow a slightly different trajectory, and so one will come here and one will come there. Now, but in reality, it's never this clean, and it's actually, they're going everywhere. And they won't precisely hit the curve. There may be a spreading in the beam, so it's unbelievably inefficient. And it's all dependent on being able to clean out those separators. These are typically made of graphite, and you can easily recover the material in that. But there's uranium everywhere in here. It's all valuable, so it's typically recovered. Here shows the side of one of the magnets. So this is a pole piece, so it's electromagnetic. magnet, and so, but they're very large pole pieces. And this one was taken from the Iraqis. And here's a picture of, they called them tracks or race tracks. And so this one, it was the first stage, which would take natural uranium up to some value. Now, one of the advantages of the EMIS method is that it separates really well. And so in the first stage, you could go from natural up to 10, 12% enriched uranium. And then the second stage could go from there up to about, it would vary, maybe 70, 80, rarely would it get to 90%. And it required, yeah, and the names, this is US terminology, alpha and beta. I think I can't remember, the Iraqis used a different terminology. And the Iraqis had trouble designing this kind of system. You do this under a vacuum. This is actually done under a vacuum, and it's a large volume, and it's hard to get to work. And they were struggling with that. They didn't know. In fact, this is a kind of an example of the problems in proliferant states that are essentially developing countries, trying to work beyond their industrial average capability. And these things have doors, and they weren't able to mass produce the doors. That every one of these units, separators, had its own individual door, and they had problems with leakage of the vacuum, which will devastate the enrichment process. And it requires a lot of people. There were 24,000 people working at Oak Ridge on this at its peak, and they had 5 of these alpha track buildings with more than one racetrack, and then four beta separator buildings. And then there were a whole slew of buildings involved in the chemical separation process associated with this, and then making the feed material. And people have likened this project to the placement of a permanent mission on Mars in a period of 4 to 5 years. So it was a huge industrial effort at the time. And here's some more pictures of them. Yeah, and this is an alpha vacuum chamber that's being taken out. And it would be slid in between the pole pieces. And then here, there were lots of women working in this, and
they didn't know what they were doing.
They didn't know what they were doing.
No idea.
Yeah,
this one woman saw the picture years later. She was like, "What?"
No, that's right. Yeah, in fact, she said, I have it right here, she said she spent 8 months of her life watching meters and adjusting dials without knowing what she was actually doing. So that's a good example of compartmentalization. And then here is, this is it's called an ion source. It creates the beam of uranium ions. And it's incredibly hard to make right. The Iraqis had terrible time with this, absolutely terrible time. It wasn't easy for the U.S., but I mean, that's, I guess the center left is Robert Oppenheimer's brother. But since it was uneconomic and required huge numbers of people, they dropped it as soon as they could. They had another process, gaseous diffusion, which was being developed. And again, it's inefficient, but it's more efficient than the EMIS. And you end up with a product that's a lot easier to deal with. They use uranium hexafluoride. It uses huge amounts of electricity. But one principle I'd like to impress you with is that the drive to build nuclear weapons justified the enormous expenses. They were willing to do almost anything. And I'll leave this to you. This is I think in one of the handouts. I mean, the idea of the terminology on gaseous diffusion is there's something called a diffuser, which is where the separating elements are located. You have to have a compressor that pushes the gas along. You're essentially pushing the gas through a barrier, and by going through the barrier, it separates the uranium isotopes slightly. And because it has a compressor, which is spinning and pushing. It uses a lot of energy. So it's very expensive process. And then here's the first gaseous diffusion plant at Oak Ridge. It was called the K25 plant. It started making enriched uranium in the summer of 1945, but it wasn't finished enough to make up to 80–90%. And what they found, though, is that if they used the gaseous diffusion plant to produce the low enriched, if they avoided the alpha stage of the EMA separator, the beta stage was a remarkable instrument to go from whatever it was, 20% all the way up to 90%, very efficiently. So they found that it's the alpha separator that's the real inefficient part. But once they could make the HEU in the gaseous diffusion plant, they shut down the EMAS program. And then because it required so much money to make the enriched uranium all the gaseous diffusion plants in the U.S. are shut down. Russia abandoned them. There's no more of these plants in the world. Yeah, here's a kind of a fuzzy picture of the first Chinese enrichment building. So it was this is 100 meters. Gives you a sense of the size. This thing is, kilometer long. So and what that means is it enriches very, very slowly. That each step is enriching just a tiny bit. So you need lots of steps. And that's a French one, which is also closed. And here you see some of the indications, the amount of heat generated. These are they have coal plants that generate the electricity, and the excess heat that's from these plants has to be dissipated through these massive cooling towers. Yeah, and there some of the other processes. I mean, I won't go through them. We have the plasma separation process was never used on any major scale. There's aerodynamic process, which South Africa used. And I couldn't find a picture on the web, but there is one in the handout, which you weren't able to make a copy to hand out. So you sent it to people.
I'm not sending it.
Okay, so it's called a vortex tube, and it literally is just a high-speed gas injected into a tube, and that causes a separation. But again, very inefficient. But South Africa used it to make HEU and tried to commercialize it, but it was so expensive that once apartheid ended and they could buy a low enriched uranium, they just shut down the enrichment program. But again, it's another case where to get nuclear weapons, they were willing to spend almost anything and develop this incredibly inefficient enrichment process. One that's been the dream of the enrichers of the world is laser enrichment. And again, with laser enrichment, it's theoretically a very simple method to separate isotopes, and you can get very good separation factors with laser enrichment. But in reality, you're really struggling with getting everything to work. It's very hard, extremely hard to do, and there was a process developed called Silex, which was actually intended to be commercialized in this country, and they decided, I think they announced this summer that they're not going to do it. And there's from a proliferation standpoint, there was worry that if they did do it, that it would rejuvenate everyone's interest in laser enrichment. And so when it was at its height in the 80s, particular, U.S. was doing it, Russia on a very aggressive scale, and then you saw it in Iraq, Iran, Pakistan, India. They're all sort of all copying and producing it. And Iran actually developed a secret laser enrichment plant, very small scale. And the way they did it is they got help from the Russians, and were able to buy key equipment from the Russians and on the commercial markets to cobble together this secret laser enrichment plant. So the worry is if Silex takes off, the technology will leak, and it could rejuvenate another method. And with laser enrichment, because it can be so effective at separating the uranium isotopes, it means you can build a much smaller plant, and it doesn't require much electricity. So if you can do it, it can lead to a smaller, easier to hide enrichment plant. Now the last one, and I'll pick this up next week. Gas centrifuges. And this one's important because it is really the only deployed enrichment method in the world today, both for making nuclear weapons material and for making low enriched uranium for nuclear power reactors. And cover more of this next week, but it's basically just a rapidly rotating tube. And it's very efficient because unlike gaseous diffusion, which required these energy intensive compressors, the gas moves from centrifuge to centrifuge based on its own actions. There's no energy required to get the gas to flow through the centrifuges one after another. So it's well, much more efficient. And it has other advantages. It separates the isotopes better than gaseous diffusion. But again, its disadvantage is that it's extremely hard to make and get to work. Because it's spinning, 300, 400, 500 meters per second. The outer wall is. You can imagine everything has to be precisely balanced. Any imbalance is going to cause some wobbling, and at those speeds, if it hits the wall, just grazes the wall a little bit, it'll if it's metal, it'll fly apart like shrapnel. So so everything has to be done with incredible precision, and you have to do many of the assembly or manufacturing steps in they're called clean facilities.